Good afternoon, everybody. My name is Barry Husk. I'm president and founder of BlueLeaf, a company that has existed for 12 years now. On m'a demandé de présenter en anglais, mais si vous avez des questions en français à la fin, ou en tout cas, gênez-vous pas. I'll tell you a little secret. Today's presentation is the most challenging thing I've had to do with ATRAPP so far, because Dana called me, or Alejandro, and they said, we want you to talk about your 12 years' work, but you have 10 minutes to do it. So I'm either going to talk fast or anyways, I hope I can keep up with things. Title of our presentation is Integration of ATRAPP into a Long-Term Rehabilitation and Monitoring Project. So this project takes place at Petit-Lac-Saint-François, which is located in the eastern townships of Quebec. It's just north of Sherbrooke, for those of you who know that area. And it's an integrated, multi-partner watershed-based rehabilitation program, and we're now in our 12th year. We started in 2007. The key message I would like to tell you is that perhaps contrary to some of the other work that's presented here, our work is mostly focused on prevention. What can we do to prevent having cyanobacteria? So some of the methods that we've been working with, primarily related to agriculture. And the watershed for Petit-Lac-Saint-François is primarily an agricultural watershed. We have installed what we call low-impact development projects. And I know Sarah is working in Three Rivers on some projects that are coming up, but we've done a fair amount of work in our watershed as well, related to capturing rain, runoff, treatment, measurement of the results. More related to agriculture, we've done a lot of work with biochar, which is a soil amendment, and we're looking at ways that biochar can reduce runoff and the efficiencies of fertilizers, both phosphorus and nitrogen. And we do a lot of work on agricultural field drainage. For those of you who aren't familiar, most of the agricultural fields in southern Quebec and elsewhere, where we grow corn and soybean, almost all of these fields, without exception, have drainage installed. So it's about 1 meter below the surface, and it assists in drying the land, getting people on the land sooner. But it's also a source of probably somewhere between 75 and 85% of the nutrients that leave agricultural fields. Some of the things that we work on for drainage is, first of all, using controlled drainage, which allows us to control the water, keep it on the land for use when we need it. The result is that we have less phosphorus and nitrogen leaving the fields. We use wood chip denitrifying bioreactors. So again, based on the drainage, we will circulate drainage water through wood chip bioreactors, which interact biologically with the nitrogen and convert it to a form which, mostly to a gaseous form, so we're reducing the nitrogen levels that are in the water, in the drainage water. A new development that we've worked on for the last 5 years or so is actually phosphorus reactors. So this is installing reactors at the end of agricultural drains at the outlet and using materials which can capture phosphorus and allow us to recycle the phosphorus back into the agricultural system. So some preliminary findings. Here you see I forgot to mention this, but we have over 500 weeks, consecutive weeks, over 10 years of data for most nutrients, and that's 12 months a year, winter and summer. So what you're looking at here is, in the case of phosphorus, the total phosphorus is the annual results in box plot from 2011. Draw your attention to the 2 vertical dotted lines. Whoops, I'm sorry, wrong button. These two lines here. So this first one is the date, represents the date that we installed denitrifying bioreactors and controlled drainage in the watershed. So we're measuring to see if there's any change in the phosphorus levels in the lake. The second line here is the date that we installed phosphorus reactors on agricultural drainage. So you can see that the trend is going in the right direction. It's going down. not only in terms of the mean average or the average for the year, but also in terms of variation. So we're getting a lot less variation and lower values. In the terms of nitrogen, again, you have the same results shown here. We have box plots for each year from 2012, and with the same two dates. This one being controlled drainage installed and denitrifying bioreactors. And this line here is phosphorus reactors with more controlled drainage. So again, you can see that things are changing in the lake, where there's the concentrations of phosphorus and total nitrogen are lower. They're going in the right direction. A couple of statistics for cyanobacteria. This one here represents the species richness, and from 2010. So you can see when we first started working there, typically we would have in the range of 20 cyanobacteria species present, and in the last few years we're more in the range of 3 to 5 species that are present. So it's a major change in terms of the species and the richness. This is another interesting change that we're tracking, and we suspect has something to do with the changes in nutrients, but there is a move towards, or a trend towards, more diazotrophic or nitrogen fixing species in the lake. And again, you can see each year there from 2012 until last summer. And last summer we had almost exclusively diazotrophic species in the lake, which was something entirely new. In terms of nutrient correlations, so what we're looking at here is, again, about 10 to 12 years of data, depending on the parameter. But we've ranked the total cyanobacteria biovolume according to Pearson correlation coefficients. So you can see the scale on the bottom here. You're looking at plus 0.6 and minus 0.6, so that's the range. But interesting to note that the highest correlations are with nitrogen in this case. And this is over a period of many years, but it's all cyanobacteria together, so it's all cyanobacteria biovolume. And you can see how it degrades here, and you have negative correlations with these ones down here. But the tendency is to always talk about how important phosphorus is, but what we're finding is that nitrogen is at least, if not more important in many cases. So that's total cyanobacteria correlations. This one here, this correlation is for one species only, in Dolichospermum, which used to be known as Anabena. But I've used the same scale here, so you can see that goes from 0.6 to minus 0.6. So you can see the correlations are really not that significant. So when we pull out one species, in this case a nitrogen fixing species, we're finding correlations over 10 years that are virtually, don't really mean that much. So obviously the correlations must be much higher with other species because the total is quite high. But in the case of Dolichospermum, there's virtually no significant correlations with the fractions that we're looking at. And I think in here we even have the molar ratio here, NP molar ratio, so it's virtually non-significant. In terms of predicting cyanobacteria blooms, this is something that we've been working on for a few years now, and we'd like to pull more into ATRAPP if we can. But when we're taking our samples on a weekly basis throughout the year, we're measuring both chlorophyll in situ and phycocyanin. And you can see the two graphs here side by side, and there's about 4 years data on there. So typically what happens is around week 29, that's starting in January, so week 29 is about the first week of August. That's when the major blooms start. And you can see from these trends here that it's similar year to year, year after year, it's always the same thing. And both phycocyanin and chlorophyll in situ seem to be good indicators for when we have a bloom. That's no good for predicting when we're going to have a bloom. So what we got to asking ourselves is, what if we were to take the ratio of one to the other and see what that does for us? So what we have here is using a ratio of chlorophyll to phycocyanin. And if we take a major move that happens usually around week 20, which is somewhere around the end of May, you can see there's a major change in the ratio between the two. And if we were to arbitrarily take a number like 200 and say once it reaches 200, well then we're getting into the danger zone, that would give us about 9 weeks of lead time, so to speak. So in terms of for someone who's operating a beach or something, it's maybe not that important, but someone who's running perhaps a water treatment plant, it might be more useful. So we're finding that ratio there is quite interesting. We have the same data for 20 other lakes, but we haven't had a chance to analyze it yet. In terms of taxonomy, while we're used to doing microscopy or doing morphological taxonomy, and we just started getting genetic taxonomy, and the first thing that struck us right off, and this is looking at one sample only, is the presence of picocyanobacteria. And this is something we were absolutely never aware of because we don't measure this, we can't with traditional microscopy. In this particular sample, which was just taken at random, it was actually 45% of the relative abundance. So this is amazing, and you can see down here, I'm sorry. The Dolichospermum and Microcystis, which are traditionally are most present in our microscopy analysis, are virtually unimportant in terms of relative abundance. So this is something that we need to examine more, I think. And just to compare, I've taken that same sample, and this is how it looks on morphological taxonomy by microscopy. So obviously there's no picocyanobacteria, and you can see the main species that are present. And by the way, for Jesse could tell you more about this than I can, but the Crococcus we didn't find on the genetic for the reasons that you could explain better. But anyways, it's just to point out the importance that we think picocyanobacteria will have, which is just not on the radar with anybody at the moment. The other issue that's come up with us, especially in the last 2 or 3 years, is the presence of toxic benthic cyanobacteria. Those of you who are familiar with Christiane Hudon's work with Environment Canada in the St. Lawrence are aware of the work that she's done on Lingbia and the importance of that cyanobacteria in that system. But we started looking for it, first of all, a couple of years ago, and we find it in the lake that we're researching on, but that led us to look at other areas, and we find it practically in every river and lake system in southern Quebec. So it's something to be aware of, and these are toxic cyanobacteria. I don't think we're doing much on this yet in ATRAPP, but I think we're perhaps underestimating the importance of these species. The last item that I wanted to mention, and this is not necessarily part of ATRAPP, although there were some people in ATRAPP who are involved in this work, and that's the presence of cyanobacteria in groundwater and also in soils. So we have a project that's where Sébastien is involved in it, and a couple of other people here with McGill, and we're looking at the importance of cyanobacteria and cyanotoxins in soils and also in groundwater, and well water as well. And I thought I'd finish by one of my favorite quotes by some people call him the founder of limnology, François-Alphonse Forel, who said, "I put to myself 2 options, create my own research lab or take for my laboratory this lake that offered me its mysteries and beckoned me to study them. So my choice was soon made." With that, I thank you.
Thank you. Any questions for Barry?
Yeah, we have a pretty good assay for saxitoxin in Lingbia, walleye. Very specific
Okay.
for saxitoxin from that creature. So,
Okay, good to know.
Some of us are working on it.
Okay,
So
good
yeah,
enough.
please feel free to contact us if you want to set
Will
something
do.
up. Yeah.
Thanks.
Other questions for Barry?
Do you know what kind of biomass proportion it would be, the fecal cyanobacteria?
I don't. It's a very good
Because
question.
it's a big number.
Yeah.
And a lot of, do you think it would be a big part of biomass?
I-
It would be an extrapolation. You have to
Yeah, yeah.
guess from the sequence. You don't know the size.
I know.
But if you could know
That-
something about the distribution of the size, and then
We probably
you
have
see the
that,
bigger
but
things under the micro. You could, I'm sure you
have
could
an idea
extrapolate some
if
kind
it's
of
significant, because it could be a
Yeah,
lot
yeah.
of copies, but not a lot of biomass.
Yeah.
Would that make sense?
Yeah, it's possible.
It's something.
That's a really interesting thing for treatment.
Yeah.
Yeah.
I'm
We,
sure
we can do some more work
How,
on that.
how, how pico are they?
How pico are they, Jesse?
À la baie-Missisquoi, en tout cas, moi, j'avais fait comparer les biovolumes avec... puis c'était négligeable, là, c'est-à-dire la biomasse des picocyanobactéries versus la biomasse de toutes les autres cyanobactéries. Je me souviens pas, mais c'est quelque chose comme 0,5% ou quelque chose comme ça, là. Ouais. Ben, je pense que je me demande si dans mon rapport que je venais de publier, à moins que ce soit l'autre que je t'avais de publier.
Par rapport aux diminutions là, de phosphore et
Oui.
de nitrate,
Oui,
c'est ça?
oui.
Est-ce qu'il y a d'autres facteurs que le fait d'avoir installé certains réacteurs ou comme la pluviométrie, par exemple?
Oui, non, exact. Ben,
Pour
nous,
expliquer ces diminutions-là.
c'est possible. Nous, on suit d'autres facteurs en même temps. Par exemple, on mesure. On fait l'inventaire de la superficie qui est en culture à bande large, là, c'est-à-dire soya et maïs. Fait qu'on sait combien d'hectares dans le bassin versant chaque année. Fait que ça, c'est un facteur. L'autre facteur, c'est le débit et le charge, parce que là, on évalue la concentration, mais on a aussi le charge. Fait qu'on est en mesure de comparer d'année en année si le charge de phosphore total est différent d'une année à l'autre ou la concentration. Mais c'est difficile de contrôler tous les facteurs, mais on peut supposer qu'une bonne partie est à cause de ces changements-là, parce qu'on a mesuré sur le champ aussi, qu'on ne voit pas là, mais à chaque champ puis à chaque installation, une mesure qui est faite. Là, on est en mesure de dire, bien, il y a une diminution de 90% ou whatever.
Petite dernière, peut-être pas, mais...
Barry, je suis curieuse de savoir, quand vous mettez les bioréacteurs, ça diminue le phosphore et l'azote dans le lac, mais est-ce que ce phosphore et cet azote restent disponibles pour les cultures ou où est-ce qu'il s'en va? Qu'est-ce qui arrive?
Bien, nous, on l'enlève après la culture. Donc, c'est à la sortie du champ. Fait que c'est des formes d'azote et des formes de phosphore qui s'en vont dans le cours d'eau et qui se rendent au lac. Fait que nous, on s'ingère entre le champ et le lac, puis là, c'est là qu'on les intercepte. Dans le cas de phosphore, ce qu'on fait, c'est qu'on l'accumule, puis on est capable de le recycler en amont sur la ferme. Dans le cas d'azote, non, parce que ça devient une forme gazeuse.
Merci, Barry.
Merci.